welcome to this problem walkthrough. Today, we'll tackle problem number 840, magic squares in grid. This problem is an interesting blend of grid traversal and mathematical patterns, requiring us to validate magic squares within a given matrix. Stay tuned as we explore different approaches to solve this step by step. In this problem, we are working with a grid of integers, represented as an MXN2D list. The goal is to identify all 3x3 subgrids within this larger grid that qualify as magic squares. A 3x3 magic square is defined as a grid where all the integers are distinct and fall within the range of 1 to 9. Additionally, there are 3 critical conditions that must be met for it to be considered a magic square. First, every row must sum to the same value. Second, every column must also sum to the same value. And third, the 2 diagonals must sum to that same value as well. The task is to write a function that returns the total count of 3x3 magic squares present in the given grid. The grid's dimensions will be between 1x1 and 10x10, and each element in the grid will range from 0 to 15. The output is a single integer representing the count of valid magic squares. For example, consider the input grid shown here. It is a 4x3 grid of integers. The function needs to locate any 3x3 subgrid within this larger grid that satisfies the requirements of a magic square. In this case, there is exactly one valid 3x3 magic square, which is found in the top left corner of the grid. The numbers in this subgrid are arranged as follows: the first row is 4, 3, and 8, the second row is 9, 5, and 1, and the third row is 2, 7, and 6. Our output for this example would be 1, indicating that one magic square was found. Let's break down why this subgrid qualifies as a magic square. First, each row sums to 15. The first row, 4 plus 3 plus 8, equals 15. The second row, 9 plus 5 plus 1, also equals 15. And the third row, 2 plus 7 plus 6, equals 15 as well. Next, each column also sums to 15. The first column, 4 plus 9 plus 2, equals 15. Similarly, the second column, 3 plus 5 plus 7, and the third column, 8 plus 1 plus 6, both sum to 15. Finally, the 2 diagonals also sum to 15. The first diagonal, from the top left to the bottom right, is 4 plus 5 plus 6, and the second diagonal, from the top right to the bottom left, is 8 plus 5 plus 2. Since all of these conditions are satisfied, this subgrid is a valid magic square. Now, consider a second example where the entire grid itself is a 3x3 magic square. The values in this grid are 8, 1, and 6 in the first row, 3, 5, and 7 in the second row, and 4, 9, and 2 in the third row. Once again, all the conditions for a magic square are met. Each row sums to 15, 8 plus 1 plus 6, 3 plus 5 plus 7, and 4 plus 9 plus 2 all equal 15. Each column also sums to 15, 8 plus 3 plus 4, 1 plus 5 plus 9, and 6 plus 7 plus 2 all give 15. Finally, the diagonals sum to 15 as well, 8 plus 5 plus 2, and 6 plus 5 plus 4. Since this grid satisfies all the necessary conditions, it is counted as a valid magic square, and the output for this example is 1. Finally, let's explore an example where the grid does not contain any magic squares. Here, all the values in the grid are identical, with each cell containing the number 5. For a subgrid to qualify as a magic square, the numbers must be distinct and fall within the range of 1 to 9. Additionally, the rows, columns, and diagonals must all sum to the same value. In this case, none of these conditions are satisfied. The numbers are not distinct, and the sums of the rows, columns, and diagonals do not match. Therefore, the output for this grid is 0, indicating that no magic squares were found. When solving this problem, it's also important to consider edge cases, such as grids that are too small to contain a 3x3 subgrid, grids with no valid magic squares, or cases where multiple overlapping magic squares exist. Ensuring that all these scenarios are handled correctly will help produce an accurate solution. To solve the problem of identifying magic squares in a grid, the brute force approach is the most intuitive starting point. Here, we systematically check every possible 3x3 subgrid within the given MXN grid. For a subgrid to qualify as a magic square, it must satisfy 2 key conditions. First, it should contain all numbers from 1 to 9 exactly once, and second, the sum of each row, column, and diagonal must equal 15. To implement this, we loop through all potential top left corners of 3 by 3 subgrids, extract each subgrid, and verify these conditions. The time complexity of this method is O(m*n), as we need to iterate over roughly m2*n2 subgrids, and verifying each subgrid is an O(1) operation. While this approach is simple and easy to code, it has a downside: it performs redundant checks and doesn't leverage any deeper properties of magic squares. As a result, it's less efficient for larger grids, making it more suitable for smaller examples. To improve efficiency, an optimized approach can be used. This method reduces redundant computations by taking advantage of the fixed properties of magic squares. Specifically, there are only 8 possible 3 by 3 magic square patterns using the numbers 1 to 9, and we can pre-compute these configurations upfront. When evaluating each subgrid, instead of rechecking all properties from scratch, we can simply match the subgrid against these pre-computed patterns. Additionally, validation shortcuts can streamline the process further. For instance, we can verify that the subgrid contains numbers 1 to 9 using a frequency array or set, and then quickly check the sums of rows, columns, and diagonals. These optimizations significantly reduce the number of operations required while maintaining the same overall complexity of O(m*n). However, this approach requires slightly more implementation effort, as we need to handle pre-computations and edge cases. Despite this, the gains in efficiency make it a more practical solution for larger grids. The optimized approach was chosen as the final solution because it strikes the right balance between simplicity and efficiency. By leveraging the fixed properties of magic squares, such as their predictable patterns and constant row, column, and diagonal sums, we avoid unnecessary computations and focus only on valid subgrids. This strategy is particularly advantageous as the grid size increases, where the brute force approach becomes computationally expensive due to redundant checks. Key observations include the fact that the magic sum for a 3 by 3 grid is always 15 and that there are only 8 valid configurations for a 3 by 3 magic square, which allows for pre-computation. Additionally, validating a subgrid is efficient, relying on simple arithmetic checks that operate in constant time. Ultimately, this approach is more scalable, efficient, and elegant, ensuring that the solution is both robust and clean. These characteristics make it the ideal strategy for solving this problem. To tackle the problem of finding all 3 by 3 magic squares within a given MXN grid, we start by understanding the requirements. A 3 by 3 magic square must use every integer from 1 to 9 exactly once, and the sum of each row, column, and both diagonals must equal 15, which is known as the magic constant. The input to our algorithm is an MXN grid of integers, and our goal is to determine how many 3 by 3 subgrids within it satisfy these conditions. To do this, we iterate over all possible 3 by 3 subgrids in the grid. Since the top left corner of any valid subgrid must fit within the bounds of the original grid, the top left corner of each subgrid can only range from row 0 to m3 and column 0 to n3. Using 2 nested loops, we iterate through each valid starting point, defined by rows I from 0 to m3 and columns j from 0 to n3. For each pair of I and j, we extract the 3 by 3 subgrid starting at that location for further validation. Once we have extracted a 3 by 3 subgrid, the next step is to validate whether it satisfies the magic square conditions. The first condition is that the subgrid must contain all digits from 1 to 9 exactly once. To verify this, we flatten the 3 by 3 subgrid into a single list and check if sorting this list results in the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9. The second condition is that the sum of each row, column, and both diagonals must equal 15. To check this, we calculate the sums of all rows, columns, and diagonals in the subgrid and store these sums in a set. If the set contains only one unique value, and that value is 15, we know the subgrid satisfies the magic constant. If both conditions are met, we count the subgrid as a valid magic square. To keep track, we use a counter initialized to 0 at the start. Every time a valid magic square is identified during the iteration, we increment this counter. Finally, after examining all possible subgrids, we return the counter as the total count of magic squares in the grid. There are several key insights that make this problem more manageable. First, a 3 by 3 magic square is highly constrained, as it must use all digits from 1 to 9 and achieve a sum of 15 in every row, column, and diagonal. These constraints allow us to reduce unnecessary computations. For instance, by simply sorting the flattened subgrid and comparing it to the fixed sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, we can quickly verify that all required numbers are present without duplicates. In terms of data structures, the input grid is represented as a 2D list, while each extracted subgrid is another 2D list of size 3 by 3. To validate the sums, we use a set to capture unique sums of rows, columns, and diagonals. This ensures that all sums match the magic constant. Finally, a simple integer variable serves as a counter to keep track of the number of valid magic squares found during the iteration process. The algorithm relies on a few key operations to work efficiently. First, we use slicing to extract each 3 by 3 subgrid directly from the larger grid, which is computationally efficient and avoids unnecessary copying of data. Next, validation involves two main checks: sorting the flattened subgrid to confirm the presence of all required numbers, and summing rows, columns, and diagonals to ensure the magic constant is satisfied. The nested loops ensure that each potential 3 by 3 subgrid is visited exactly once, leading to a time complexity of O, M2, N2, where M and N are the dimensions of the grid. Since validating each subgrid involves constant work, the overall complexity includes this constant factor. The space complexity is minimal, as we only use a small amount of additional space for the sums and the set. A few edge cases to consider include grids smaller than 3 by 3, in which case no subgrid can exist and we immediately return 0. Grids containing numbers outside the range 1 to 9 will fail validation automatically. Finally, overlapping magic squares are handled correctly since each subgrid is validated independently, ensuring no double counting or missed cases. Here, we begin by defining a class solution and a method number magic squares inside that takes a grid as input. Inside this method, there's a helper function is_magic, which checks if a given 3 by 3 square meets the criteria for being a magic square. First, it flattens the square into a list of numbers and verifies that these numbers are unique and fall within the range of 1 to 9. If this condition is not met, the function immediately returns false. Next, it checks whether the sums of all rows, columns, and both diagonals equal 15, which is the defining property of a magic square. If all these conditions hold true, the function returns true. After defining the helper function, we determine the dimensions of the grid and initialize a counter count to 0. This counter will track the number of magic squares we find. Now, to identify all possible 3 by 3 subgrids within the given grid, we use nested loops. The outer loop iterates through the rows, stopping at M2 to ensure we don't go out of bounds, while the inner loop does the same for the columns, stopping at N2. For each valid starting position, we proceed to extract the 3 by 3 square. The 3 by 3 square is constructed by taking the current row and column index from the nested loops and slicing out the appropriate rows and columns from the grid. This is done by creating a list of lists, where each inner list represents a row of the square. Once the square is assembled, we pass it to the is_magic function to determine if it satisfies the magic square conditions. If is_magic returns true, we increment the count by 1. This process continues for every possible 3 by 3 subgrid in the entire grid. Finally, when all iterations are complete, the method returns the count, which represents the total number of magic squares found in the input grid. Here, we begin with the main function number magic squares inside that takes a 2D grid as input and aims to count the number of magic squares within it. We first determine the dimensions of the grid using M and N, representing the number of rows and columns respectively. A variable count is initialized to 0 to keep track of the valid magic squares we find. To examine all possible 3 by 3 subgrids within the grid, we use nested loops. The outer loop iterates through the rows, stopping at M2 to ensure there's enough space for a 3 by 3 grid, while the inner loop does the same for the columns, stopping at N2. For each subgrid, we call the helper function isMagic, passing the grid and the top left corner of the current subgrid. If isMagic returns true, we increment the count. Finally, the function returns the total count of magic squares. Now, let's look at the helper method isMagic, which performs the validation for each 3 by 3 subgrid. The first step in this method is to verify that all numbers within the subgrid are unique and within the range of 1 to 9. To achieve this, we use a Boolean array called scene with 10 elements, initialized to false. We then iterate through each cell of the 3 by 3 grid and check whether the number is within the valid range and hasn't been seen before. If any number fails this check, the function immediately returns false. Once we've ensured that all numbers are unique and within the range of 1 to 9, the next step is to verify the magic square property itself. This involves checking that the sum of the rows, columns, and diagonals equals 15. We calculate the sums for each of the 3 rows and store them in sum 1, sum 2, and sum 3. Similarly, we compute the sums for each of the 3 columns, storing them in col 1, col 2, and col 3. For the diagonals, we calculate diagram 1 as the sum of the top left to bottom right diagonal, and diagram 2 as the sum of the top right to bottom left diagonal. Finally, we return true only if all these sums are equal to 15. This ensures that the subgrid satisfies the magic square condition. If any of these conditions fail, the function returns false. By combining this validation logic with the iteration in the main function, we successfully identify all magic squares in the given grid. Here, we begin with a simple grid example to understand how the solution works step by step. The input grid is a 3 by 4 matrix, and our goal is to identify all 3 by 3 subgrids that qualify as magic squares. First, we initialize some variables. The dimensions of the grid, m and n, are set to 3 and 4 respectively. We also initialize a counter, count, to 0, which will keep track of the number of magic squares we find. Next, we start iterating through all possible 3 by 3 subgrids. For the first subgrid, located at I equals 0 and j equals 0, we extract the 3 by 3 section of the grid, which looks like this: 4, 3, 8, 9, 5, 1, 2, 7, 6. This subgrid will now be evaluated to check if it satisfies the conditions of a magic square. To determine whether the extracted subgrid is a magic square, we use the helper function is_magic. First, we flatten the subgrid into a single list of numbers: 4, 3, 8, 9, 5, 1, 2, 7, 6. These numbers are unique and fall within the range of 1 to 9, which is a critical condition for a magic square. Next, we calculate the sums of each row, each column, and the 2 diagonals. All row sums are 15, all column sums are 15, and both diagonal sums are also 15. Since all conditions are satisfied, we increment the count variable to 1. We then proceed to check the next possible subgrid, located at j equals 1. For this subgrid, which is 3, 8, 4, 5, 1, 9, 7, 6, 2, the flattened numbers 3, 8, 4, 5, 1, 9, 7, 6, 2 are still unique and within the range of 1 to 9. However, the row and column sums are not all equal to 15, so this subgrid is skipped. After iterating through all possible subgrids in this example, we find that the final value of count is 1. This means there is only one magic square in the given grid. The output for this example is therefore 1. Now, moving on to another example, we consider a grid that does not contain any magic squares. The input grid here is a 3 by 3 matrix: 1, 2, 3, 4, 5, 6, 7, 8, 9. As before, we initialize the variables m and n to 3, and set count to 0. Since the grid is exactly 3 by 3, there is only one possible subgrid to consider, which is the grid itself: 1, 2, 3, 4, 5, 6, 7, 8, 9. For this subgrid, we start by flattening the numbers into a list: 1, 2, 3, 4, 5, 6, 7, 8, 9. These numbers are unique and fall within the range of 1 to 9, so they pass the first condition. However, when we calculate the sums of the rows, columns, and diagonals, we notice that not all of them are equal to 15. Specifically, the row sums are 6, 15, and 24, while the column sums are 12, 15, and 18. The diagonal sums are both 15, but since the row and column sums do not meet the magic square condition, this subgrid is not valid. Since there are no other subgrids to evaluate, the final value of count remains 0. The output for this example is therefore 0. Now, let's consider a larger grid where we can find multiple magic squares. The input grid is a 4 by 5 matrix: 4, 3, 8, 4, 9, 9, 5, 1, 9, 5, 2, 7, 6, 2, 7, 4, 3, 8, 4, 3. Once again, we initialize the variables m and n to 4 and 5, and set count to 0. We then begin iterating through all possible 3 by 3 subgrids. The first subgrid, located at I equals 0 and j equals 0, is 4, 3, 8, 9, 5, 1, 2, 7, 6. Using the is_magic function, we determine that this subgrid is a valid magic square, so we increment count to 1. Next, we evaluate the subgrid at j equals 1, which is not a magic square. We continue this process, skipping invalid subgrids, until we reach the subgrid starting at I equals 1 and j equals 2. This subgrid, 8, 4, 9, 1, 9, 5, 6, 2, 7, is another valid magic square. Since the subgrid at I equals 1 and j equals 2 satisfies all the conditions of a magic square, we increment count to 2. After completing the iteration through all possible subgrids in the grid, we find that the final value of count is 2. This means there are 2 magic squares in this larger grid. The output for this example is therefore 2. To analyze the time complexity of our solution, we start by understanding the outer loop structure. The algorithm iterates through all possible 3x3 subgrids within the given m by n grid. The outer loops determine the starting positions for the top left corner of each subgrid. For the subgrid to fit entirely within the grid, the I-coordinate can range from 0 to m3, giving m2 possible values, and the j-coordinate can range from 0 to n3, giving n2 values. This results in a total of m2 multiplied by n2 iterations for the nested loops. Within each iteration, the subgrid extraction process involves accessing exactly 9 elements from the grid, which takes constant time, or O1. This sets the stage for the operations performed inside each loop iteration. Now, focusing on the operations within each iteration, the is_magic function is key to verifying if the extracted subgrid is a magic square. This function includes a uniqueness check, where the 3x3 matrix is flattened into a 1D list and sorted. Flattening involves accessing 9 elements, which takes O1, and sorting such a small number of elements also runs in O1. The function then performs some checks for rows, columns, and diagonals. Each of these checks processes exactly 3 elements, and since there are 8 checks in total, the time required is constant at O1. Therefore, the is_magic function runs in O1 time for any given subgrid. Combining this with the outer loops, where each iteration involves constant time operations, the overall time complexity becomes O(m2) n2 O1. Simplifying further, we arrive at O(m*n), ignoring constants for asymptotic analysis. Turning to space complexity, the memory usage of our solution is driven by temporary storage during execution. First, the extracted 3x3 subgrid is stored in a temporary list, requiring space for 9 elements. This contributes O1 space since the size of the subgrid remains constant. Similarly, during the is_magic check, the subgrid is flattened into another 1D list of 9 elements, which also uses O1 space. Additionally, auxiliary variables like the loop indices and counters use a fixed amount of memory, which is again O1. Importantly, the algorithm does not allocate any space that scales with the size of the input grid. As a result, the total space complexity of the solution is O1, signifying that the memory usage remains constant, regardless of the input grid size. When we compare this optimized approach to a brute force method, the efficiency becomes even clearer. A brute force solution would involve generating all possible 3x3 matrices with numbers 1 through 9, which results in 9 factorial, or 362,880 permutations. Checking each permutation against the grid would be computationally prohibitive, especially for larger grids. By contrast, the current solution avoids this combinatorial explosion by directly evaluating each subgrid in the input grid. This reduces the time complexity to O(m*n), a significant improvement. Additionally, the space complexity for this approach remains O1, as it does not require additional memory dependent on the input size. The time complexity is consistent across all cases best, average, and worst, because the algorithm always processes all m2 by n2 subgrids. The mathematical basis for these complexities is straightforward. The nested loops drive the O(m*n) time complexity, while the constant space usage avoids dynamic memory allocations. This makes the solution both efficient and scalable for larger inputs. When solving the magic squares in a grid problem, there are a few common mistakes to watch out for. First, always ensure the grid dimensions are valid. A magic square requires at least a 3 by 3 subgrid, so attempting to check smaller grids will result in runtime errors. Next, be thorough when summing rows, columns, and diagonals. All of them need to have the same sum for the subgrid to qualify as a magic square, and overlooking even one can lead to incorrect results. Another critical point is ensuring that the numbers in the subgrid are unique and fall within the range of 1 to 9. A valid magic square uses each of those digits exactly once, so skipping this check is a common logic error. Also, consider the efficiency of your loops. Inefficient nested loops can lead to redundant computations, so aim to optimize your traversal. Finally, don't assume the input grid values will always fall in the expected range of 1 to 9. Grids with numbers outside this range cannot form a magic square, so handling such cases early can save unnecessary computation later. Now, let's discuss some insights that are particularly useful in interviews. Recognizing patterns is key. Magic squares are defined by properties like constant sums and the use of unique digits. Demonstrating your ability to identify and systematically apply these constraints is often what interviewers are looking for. Optimal traversal is another important point. For example, you can highlight how breaking early when a subgrid fails a property can reduce unnecessary checks and improve efficiency. It's also essential to discuss edge cases, such as what happens with grids smaller than 3 by 3, grids containing negative numbers, or grids with duplicate values. This shows that you've thought about the problem comprehensively. Finally, be prepared to explain trade-offs, such as the balance between implementing a brute force approach for readability versus optimizing the solution for efficiency. If you're looking to broaden your understanding, consider exploring related problems like valid Sudoku, where similar grid validation is required, or rotate image, which involves manipulating a grid structure. Problems like number of islands and set matrix zeros are also great for learning efficient grid traversal and updates while maintaining constraints. There are several approaches to solving the magic squares problem, each with its own advantages and trade-offs. The simplest is brute force, where you iterate over all possible 3 by 3 subgrids and check their rows, columns, and diagonals. This method is straightforward to implement, but it's inefficient for large inputs due to its high computational cost. A more optimized approach is the sliding window technique. Here, you can reuse sums from overlapping rows or columns as you move across the grid, which reduces redundant computations. While this makes the solution faster, with time complexity reduced to m*n, it does come at the cost of increased implementation complexity. Another useful strategy is incorporating an early exit mechanism. For instance, as soon as a subgrid fails any magic square property, you can skip further checks for that subgrid. This improves runtime for invalid cases, though it doesn't change the overall worst-case complexity. Each of these approaches has its place depending on the constraints and priorities of the problem you're solving. Great job! We've reached the end of this problem walkthrough. Today, we learned how to validate magic squares within a grid and explored the brute force approach. We also discussed key concepts like grid traversal and optimization. Thanks for watching. Be sure to like and subscribe for more tutorials. Keep practicing and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!